All right, let's look at the sample test for chapter 4. So to begin with, number 1, they say, given the graph that we have over here, what are the local and absolute maxima and minima? All right, so for our local or relative maximums and minimums, you can see right here we have a relative maximum at negative 2, 2. We have a relative minimum at 0, negative 1, and we have a relative maximum at 2, 2. Relative maximums and minimums do not occur at endpoints. For absolute maximums and minimums, they can occur at relative local extrema, or they can occur at endpoints. It literally is the one absolute lowest point on the graph. So my absolute minimum would be negative 4, negative 2. And then my absolute maximum would be negative 2, 2, and 2, 2. And it is the one absolute highest point on the graph. The absolute highest is the y value of 2. It just happens to occur 2 different places. So that's not a contradiction. I do still have an absolute maximum value. It just happens at 2 places. So you can give the whole ordered pair for these. That's perfectly fine. If for some reason you're asked to only give one value, the maximum or the minimum is the y value. Where it occurs is the x value. All right, then let's look at number 2. For number 2, we want to find our critical numbers. So remember that critical numbers are where the derivative equals 0 or where the derivative doesn't exist. So let's find our derivative first. So we're going to say denominator, x minus 5, times derivative of numerator, 6x, minus numerator, times derivative of denominator. So the derivative of x minus 5 would just be 1 minus 0, or 1, all over the denominator squared. So to simplify my numerator, I'm going to distribute the 6x. So 6x times x is where we get the 6x squared. And then negative 5 times 6x gives us the negative 30x. Negative 3x squared times 1 is the negative 3x squared. So 6x squared minus 3x squared gives us 3x squared minus 30x, all still over the x minus 5 squared. So we said critical numbers are where the derivative equals 0 or where it doesn't exist. So where this fraction is going to equal 0 is where its numerator equals 0. The only way a fraction equals 0 is where the numerator is 0. So that's what we're going to do right here. We're going to set the numerator equal to 0 to find where the derivative is 0. Then the derivative is also, the critical number is also where the derivative doesn't exist. So think domain. Think about 0 in the denominator or negative under an even indexed radical. So this derivative doesn't exist where the denominator equals 0. So when we set our numerator equal to 0, I took out my greatest common factor and set each of my factors equal to 0. And then when I set my denominator equal to 0, I'm going to get x equals 5. It's a double root, but that's not relevant right now. That's really important when we look at our sign graphs. So critical numbers of 0, 10, and 5. All right, so then let's look at number 3. When we want to find the absolute maximum and minimum on a closed interval, so what we mean is we do have endpoints, then absolute maximums and minimums could occur at those endpoints, or they could occur at a relative maximum or minimum. So we want to first go through and find our relative maximums and minimums, same thing we were doing just a second ago with the critical numbers. And then we're going to check those against our endpoints. So to begin with, to find for x squared plus 3, to find my critical numbers, I'm going to take the derivative and set it equal to 0. And so that gives me 0. So again, critical numbers where the derivative equals 0 or where it doesn't exist. Well, there's nowhere this 2x is not going to exist. So 0 will be my only critical number. So I'm going to take 0 and I'm going to plug it back into my original function because I want to see like what's its y value, its maximum or minimum value on that interval. All right, and then I'm also going to plug in the two endpoints, negative 1 and positive 4. And again, plugging those back into the original function as well. So when we plugged in, we got 3 for 0, 4 for negative 1, and 19 for 4. So the one absolute highest value is 419, and the one absolute lowest value is 0.3. All right, then for number 4, they ask us to find everything, right? So first off, we want to find critical numbers, same thing we've just been doing. Intervals of increasing and decreasing, local maximums and minimums. We get all that from the first derivative. Concave up and down and point of inflection we get from the second derivative. So let's start with taking our derivative. So if we take the derivative of x cubed minus 6x squared, we're going to get 3x squared minus 12x. So I'm going to find my critical numbers. So set that derivative equal to 0 and solve, and I'll get 0 and 4 for my critical numbers. There is no place this derivative does not exist, so that's going to be my only critical numbers, 0 and 4. So I'm going to come over here and make a sign graph for the first derivative. Good idea to label it here just to keep up with it. So I'm going to plot my critical numbers of 0 and 4, and then I'm going to pick a test point. So I'm going to pick positive 1. If I'm trying to figure out where the first derivative is positive and negative, I'm plugging that test point into the first derivative. So I'm going to plug 1 into my first derivative, and when I do, I get a negative value, negative 9. Then when I cross a single root, the sign changes. Cross a single root, the sign changes. If it had been a double root, the sign would have changed twice, so it appears to not change at all. So now looking at my first derivative sign graph, I know anywhere the first derivative is positive, my function is increasing. Anywhere it's negative, the function is decreasing, and again, positive increasing. So that's how we know that it's increasing from negative infinity to 0 and from 4 to infinity, and it's decreasing from 0 to 4. Then the first derivative test says anywhere your derivative changes from positive to negative, you're going to have a relative maximum, and anywhere it changes from negative to positive, you're going to have a relative minimum. So I know I'm going to have a maximum at 0 and a minimum at 4. They are the maximum and minimum on the original graph. So to find the y value that goes with them, I plug back into the original function. So when I plug 0 back into my original function, I get 0. And when I plug 4 back into my original function, I get negative 32. So there's my relative maximum and minimum. All right, then we're going to duplicate that with our second derivative. So here was my first derivative right here. So let's take the derivative of that for our second derivative. And again, we're going to do the same thing. Set the second derivative equal to 0 and solve. And then see where the second derivative doesn't exist. It exists everywhere. So the only value that I'm going to get from my sign graph is a positive 2. So I'm going to pick a test point like 0 to plug in. I'm trying to figure out where my second derivative is positive and negative. So when I use my test point of 0, I plug it into the second derivative. So when I plug 0 into this second derivative, I get a negative 12. So if it's negative here, cross a single root, the sign changes. So here's the sign graph for my second derivative. From that, I know anywhere the second derivative is negative, I'm concave down, so negative infinity to 2. Anywhere the second derivative is positive, I'm concave up, so 2 to infinity. Anywhere I change from concave up to down or down to up, I'm going to have a point of inflection, so where my derivative changes here. So I have a point of inflection at 2, and again, that is a point on the original function. So I'm going to take 2, and I'm going to plug it back into this original function up here, and I get negative 16. So my point of inflection where the concavity changes is negative 16. To negative 16. All right, then for number 5, we want to find all of our horizontal and vertical asymptotes. Now, the practical way that we did this in college algebra was first you had to make sure you had no common factors, meaning I don't have like an x plus 1 in the top and an x plus 1 in the bottom that I could cancel out. But once it's in its lowest terms and there are no common factors, the way that we did this in college algebra was we compared the degree of the numerator and denominator. So when the degree of the numerator was larger than the denominator, you did not have a horizontal asymptote. When the degree of the numerator was less than the denominator, you had a horizontal asymptote. It was y equals 0. Don't just tell me 0. Make sure you tell me y equals 0. 0 is a point. Y equals 0 is a line, an asymptote. And when the degree of the numerator equaled the degree of the denominator, then we said y is equal to the leading coefficient of the numerator over the leading coefficient of the denominator. So for ours, our degree of the numerator is 2, degree of the denominator is 2. So since they're equal to each other, it's going to be y equals leading coefficient over leading coefficient. So leading coefficient here is 1, leading coefficient here is 1. So that's where we get our horizontal asymptote. The other way that we could do that is we learned that the calculus method for that is take the limit as x approaches infinity or negative infinity of your function, and the answer that you get will be your horizontal asymptote. So the way that we did this was we divided everything by the highest power of x in the denominator. So I have an x squared in the denominator, so we're going to divide everything by that x squared. So you can see right here we've just gone through and taken each of those terms and divided them by x squared. So x squared divided by x squared is going to give me 1. 3 over x squared stayed the same. X squared over x squared is going to give me 1. And 1 over x squared stayed the same. So now when we're taking the limit approaching infinity, the limit of a constant is that constant. When you're approaching infinity, if you have a number divided by a variable, that limit is always 0. And our reasoning there is the numerator staying the same, the denominator is getting larger and larger, the overall fraction is going to get smaller and smaller and go to 0. But we also have a property that tells us if you're taking the limit approaching infinity of a number divided by a variable, it's always going to be 0. All right, then down here in the bottom, limit of a constant is that constant. Limit of a number divided by a variable is 0. So that's going to leave me with 1 over 1. So again, you can see we're getting the same answer either way that you do this. All right, vertical asymptote is where, again, when you have no common factors, got to check that first, it's where your denominator is equal to 0. So if we come back up here, our denominator was x squared minus 1. So let's set our denominator equal to 0. And that's going to give us plus or minus 1. So we'll have vertical asymptotes at 1 and negative 1. And the calculus way to check that is when I take the limit approaching 1 or negative 1, I have to get a limit of either infinity or negative infinity. I can approach from the left or from the right, but I have to get a limit of infinity or negative infinity for there to be a vertical asymptote there. All right, then for number 6, we want to look at a variety of different limits. So for this first one, for our limits, we always want to start with direct substitution. So I'm going to plug in infinity. So I'm going to have infinity cubed, which is infinity, over 4 minus infinity squared. So for that one, I'm going to have infinity over negative infinity. I could use L'Hopital's there. I also could use the method that we used earlier where we divided everything by the highest power of x in the denominator. So either way you want to go, if we divide everything by the highest power of x in the denominator, the x squared, you can see each of those terms divided here. All right, so that's going to leave me with x in the numerator, and then here 4 over x squared, and here x squared over x squared would be 1. So now when I plug in, I'm going to have infinity in the top. Down here, number divided by a variable is 0. Limit of a constant is that constant. So I'm going to have infinity divided by negative 1, or negative infinity. All right, then for b, when I plug in infinity, I get infinity minus infinity. That is an indeterminate form. I don't know what infinity minus infinity is. I don't know if it's 0. There's no way to figure that out. So I want to use anything in my algebraic bag of tricks I've ever learned in all my life to try to rewrite this. We could factor, we could rationalize. So we took out the greatest common factor, and then when we plug in infinity here, and 8 minus infinity would be a negative infinity. So infinity times negative infinity would be negative infinity. Something getting infinitely larger without bound times something getting infinitely larger without bound is infinitely larger without bound. Positive times negative is a negative.